1.4 lesson, part 2. This is going to be piecewise functions. So we'll look at the features of those piecewise functions and graph them and look at their domain and ranges. So a piecewise function is just a function that's defined by multiple sub-functions. And each of those functions has a certain interval of the main function's domain. So it's a function that's in pieces, and each piece has its own specific domain. So if we look at the piecewise function here in example 1, we see a linear piece here on the left and a quadratic piece here on the right. So question A is asking us for the domain of just the linear piece, straight line linear piece of that function. And that domain, left to right, on the left, that arrow's going left forever. And on the right of this piece, it stops at x equaling -1. Now on that -1, it's an open circle. So our domain of the linear piece is -infinity to -1. Using parentheses on the -infinity because we don't ever touch -infinity. Using the parentheses on the -1 because it is an open circle. Then for part B, the quadratic piece, we're looking for its domain. So this curve, just that quadratic piece, its x starts at 1, and that is a closed 1, filled in circle. So it is a closed 1. We'll use a bracket. And that domain continues all the way left forever. I meant all the way right forever. So 1 to infinity with a bracket on that 1. Then question C wants the domain of the entire function, both pieces together left to right. So we know the left starts at -infinity. The right, as we move to the right, it looks like there might be a gap at x equaling -1, but that x value of -1 does get used. So because it does get used, there's not a break in the domain of the whole function. This domain is -infinity to +infinity, which can also be written as all real numbers. That capital R with an extra stick on the side. Now, another thing we talk about with these functions a lot is intervals of x, where the function increases versus decreases. So the function increases left to right if it's going up. So we see a couple places where this function does increase. Starting on the left, moving to the right, that entire linear piece increases. When we start over with the quadratic, it goes down first, but then starts going up again. So each of those pieces is a stretch where the graph is increasing. So we need the x values, the domain of that increase. So the piece on the left is from -infinity to -1. Then the piece on the right does not start increasing until x is 0. So make the u, and then 0 to infinity, that graph will increase. So that leaves a little piece that is decreasing, and that little piece is right here. This little piece is a decrease. The x is just between -1 and 0. Make that graph decrease. Okay. At 0, because that's where it changes direction, we don't consider it increasing or decreasing. It's just a value. So on intervals of increase, decrease intervals, use parentheses for open, not the brackets. Not the brackets for closed. Use just the open parentheses. Now, let's look at example 2, and we're going to graph this. So, to graph this, we need to plot the points, okay? And then we need to connect just the piece of the domain that we're using. So, remember f of x is y. So this first piece of this function is y equals x squared. Any x that is squared is quadratic. It's going to make a parabola. This one, being y equals x squared, has no transformations. So it is just the parent function. Meaning, when we go to graph this, we can just graph y equals x squared. If we start at 0, 0 squared is 0. Vertex is 0, 0. Go across to 1. 1 squared is 1. 1, 1. Go across 2. 2 squared is 4. 1, 2, 3, 4. So 2, 4. Go to 3. 1, 2, 3. 3 squared is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And here is the positive side of this quadratic. Remember, quadratic is perfectly symmetrical, so it will reflect to the other side. This is the parent function. Now, this is the whole parent function, not just the piece we need. The piece is given to you by this. X greater than or equal to 1. So, because it's greater than or equal to, we will use a closed circle. And from that closed circle, because it says greater, x's get greater on the right. So from that x value of 1, we'll move to the right. So on the graph, when x was 1, when x is 1, here was that y. And we're following this graph to the right. As it goes to the right, it does happen to increase. It's going to curve up, and it's going to keep going. Don't just stop where the grid ends. It does keep going. And there is the first piece of the function. If you want to erase the dots we didn't use, that's fine. There is your piece of the function. Now, we need to graph the other piece of the function. Just switch colors on it. Look at what we have. And we're given y equals negative x plus 1. If it is a single power of x, it's just a line, like y equals mx plus b. It is a line. So we're going to start on the y-intercept, which is positive 1. That slope is negative 1 or negative 1 over 1. There's lots of 1s here. So we're going to plot those dots first, and then we'll look at the piece of the function we want to use. So just graphing the line, y-intercept was positive 1. Slope was negative 1. So that's down 1, right 1, down 1, right 1. Keep going, down 1, right 1, as far as we need to. Then go up 1, left 1. Up 1, left 1 for the other dots. And here's our line. It has a y-intercept at 1, positive 1, and it has a slope of negative 1. Now, the piece of this function that we're using is given to us by this piece, this part, x less than 1. Because it's less than, not less than or equal to, it is an open circle. And because it's less, it goes to the left. Less goes to the left. So from that x value of 1, we need to find where we are. Okay, on the line, find where x is 1. It happens to be 1, 0. That piece on our function is an open circle. So I erased the dot and made it open. And because it said x less, we're going to the left. So I'm following this line to the left and out forever and ever and ever. So there's the other piece to our graph. We can erase the dots that we didn't use if you want to. You can leave them there. It really doesn't matter. Now, there's our graph. We want to talk about the domain and range. The domain on the left definitely starts at negative infinity. The only place there could possibly be an open is here at x equaling 1. But if we look at the quadratic piece, it does use an x value of 1. So there is not a break in the domain at 1. There is not a break. So it does continue all the way to positive infinity. And another way to write that again is all real numbers. Range always goes from bottom to top. The bottom y value of this graph is here. That y value is 0. That 0 is open. Nowhere else on that graph does a value of y equaling 0 get used. So we start at 0 with an open, and both pieces continue up forever. So that's 0 to infinity. Then we can talk about increase and decrease intervals. Okay, function is increasing, going up left to right on this this piece on the right. This is an increase. That domain is from 1 to infinity. The x's are from 1 to infinity. Then the decrease, this left side of the graph is decreasing, starting on the left. As we go to the right, it goes down. So negative infinity until 1. And remember, we always use parentheses, not brackets, on increase-decrease intervals. So there's our piecewise function. There's our domain and range and increase-decrease. So let's try another one. Let's take a look at B. Okay. On B, again, we have two pieces. First piece has this x squared. Yeah, it's x minus 3. It's in parentheses. The square on the outside. So it is a quadratic. It is a quadratic. And this minus 3 in the parentheses has shifted this to the right 3. Yes, that feels backwards. Inside the parentheses, it does feel backwards. So this vertex of this parabola shifted 3 units to the right. So 3, 0 is our vertex. 3, 0 is the vertex. So we're going to come over here on the graph, plot our vertex at 3, 0. And then what we can do from here is treat that vertex like 0, 0 and graph the parabola from that vertex. Instead of graphing the parent function and moving it, we can graph from the vertex. So if we go across 1, up 1, 1 squared is 1. If we go across 2, 2 squared is 4. So we go up 1, 2, 3, 4. Across 3, 3 squared is 9. Up 9. If we were to go across 4, 4 squared is 16. 16 won't fit on the graph. So that's as far up as we can go. So here's the positive side. Reflect this across our line of symmetry to get the other side. And this is the parabola shifted 3 units right. Now, the piece of the function that we were using is only x greater than 0. So, because that's a greater than, not a greater than or equal to, we do an open circle. Because it's greater, we go to the right. Greater, x's get greater, going to the right. So we need to find our value where x is 0. Just look at the graph. Where x is 0, that y was that positive 9. That needs to be an open space. So I'm going to erase it and make that an open circle. And we go right. As this graph goes to the right, it goes down to the vertex, changes direction and goes up, and it will continue going up forever. It won't just stop at the edge. So there's our first piece. Now, the other piece is 2/3 x plus 4. It's a single power of x. It's a line. It's y equals mx plus b. So our b, our y-intercept, is going to start at 4. Our slope is 2/3. Slope is always the coefficient of x in a line. So slope of 2/3. We're going to start that y-intercept at 4. 2, 3, 4 is the y-intercept. And then that slope of 2/3 goes up to right 3. Up to right 3. Do that as many times as it will fit. Okay, then we need to turn around and go the other direction. So we'll go down to left 3. Down to left 3. So there's the line. And we need to look at what piece of that line we need to use. Yeah, those aren't coming off. So the piece of the line we're using is where x is less than or equal to 0. That's an equal to, so it is a closed circle. Equal to is a closed circle. And because it says less than, we go left. So on this line where x is 0, our y was this 4. And we need to move to the left. So following this graph to the left, there's the rest of the piece. And again, you can erase the dots you didn't need if you want to. So here's our piecewise function. Talking about domain, the only place there could be a break might be at 0. But if we notice, 0 does get used by the linear green piece of the function. So there's no break in the domain. Domain negative infinity to positive infinity. Or you could write that as all real numbers. Range goes from bottom to top. That left piece is going down forever. The right piece is going up forever. Only place there might be a gap is at y equaling 9, but y equals 9 is covered by a different point here. So that y value of 9 does get used. There's no gap in the range. So negative infinity to positive infinity, or all real numbers. Talking about increase, decrease, start on the left, look at what direction things are going. We start on the left of this graph, immediately starts going up. That section is an increase. That domain is negative infinity to 0, where that piece ends. Then, when we start the function over again on the quadratic piece, it's going down. This piece of the graph is a decrease. That domain is from the 0, where we started over, to the vertex, which is at x equaling 3. So that section decreases from 0 to 3. After that vertex of 3, beyond that vertex of 3, the graph increases again. It's going up. So we'll add a piece to the increasing interval from 3 to infinity. Remember, on increase, decreasing intervals, we use parentheses, not brackets. Brackets might be needed for domain and range, but we don't use them on increase, decrease intervals. So let's look at another one. Let's look at C. Both of these are quadratic. They both have an x term that's being squared. X squared gives us the quadratic function. So, in terms of graphing that, if we look at this first one, it is a parabola. It opens upward. Transformations, that +1, it feels backwards. That moved left 1. That -2 moves down 2. So this vertex is at -1, -2. -1 left, -2 down. So, don't know why that's there. -1, -2 is the vertex. From here, pretend that that vertex is 0, 0, and plot the points of the function. Okay, 0, 0. It's a parabola, so we're squaring to get the y. Across 1, 1 squared is 1. Across 2, 2 squared is 4. So we go up 1, 2, 3, 4. 3 squared is 9. If we go across 3, we go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And this y value is 7. That's the y value on the axis. It's up 9 from the vertex. We went across 4. We would need to go up 16. 16 won't fit on the graph, so we can stop there. We need to reflect this over our axis of symmetry. And here is the parabola. Now, again, we're only using a piece of this parabola. We're using where x is less than or equal to 2. That or equal to means we do a closed circle. That less than means we go left. So, we need to find where x is 2 on this graph. And where x is 2, that y up here was 7. We follow that to the left. And here is our function, this piece of it. For the other function, it is also quadratic. We'll need to use similar process to graph it. Key thing we need to look at here, this negative reflects that graph. So this graph will open downward. It's a downward facing parabola. Parabola because of the x term being squared. Down because that reflection happened. Now, transformations -2 on the inside moves right to, yes, that feels backwards. And we need to move down 5 for that -5. So this vertex will be at 2, 5. 2, 5. So we will come over to our, I did write -5, didn't I? That's down 5, so it's a -5. That vertex is 2, -5. So 2, -5 would be here. We use the 0, 0, use that vertex as 0, 0, and plot the points. Here's our pretend 0, 0. Go across 1. 1 squared is 1, but we're going down 1. Go across 2. 2 squared is 4, so we go down 1, 2, 3, 4. If we were to go across 3, we would need to go down 9. Down 9 won't fit, so this is as far as we can go here on the grid we have. Reflect on the other side of the axis, and here is where that parabola lies. Again, we're not using all of it. We're only using one piece of it. The piece that we're using is x greater than 2. So on that 2, it's going to be an open on that 2, and then we will go to the right because that said greater. So where x is 2 happens to be the vertex of our graph. So it won't always be. That 2 on this piece needed to be an open, so I'm going to erase it and make it open. So from here, we needed to go to the right, so we will follow this to the right. And here is our piece. More of this in part 2. See you in a minute.